All right, so last time we talked about shortest path. Um, and if you remember, we were using Dijkstra's algorithm to do that. And so that was a way to look at not just like the number of vertices that we go through to get from one to another, but to take into account an edge weight as we did that. And the idea being we wanted to optimize that weight. And so usually that weight would represent like a cost or maybe distance or something that we want to minimize as we move from one vertice to another. And so we saw that Dijkstra's algorithm is a way to do that. It's a greedy algorithm, but it is optimal, and it will give us the shortest path, where shortest path being the lowest cost path in this case. So, kind of talking about what we've seen of graphs so far. We started out looking at just what is a graph, the idea being that it's just these nodes and edges, right? And kind of, if we think about it, every data structure we've looked at that is a linked data structure can be a graph, right? Because it's just things that are linked together. We started with graphs that were either a multigraph or a simple graph, and we narrowed it down to focusing on the simple graph, which just meant no self-loops and no repeated edges between the vertices. And then within the simple graph, we kind of went further and said we could have these directed edges like this, or we could have undirected edges. And typically, undirected edges meaning you could travel either way if you're going from one vertice to another. The directed edges indicating you can only go from this one to that one with the directed edge. And then we went even further with that, and we said, well, you could also have these edges represent something. So it seems kind of obvious that the vertices represent something, whether that be like a city on a map, or if it is an account on a social network. You have a bunch of these entities, and you link them with these edges, but the edges could have characteristics too, so we call them weights. And we also mentioned we could name the edges if we wanted to. And so you can think about all the different applications where this could be applied, and you can think about that this may not just be like a single value, right, in a real world application. It may be like a vector of values. So it may characterize a lot of different relationships between the nodes. And so typically the weights are considered in our different algorithms for when we're traversing the graph, for measuring different things. And so then we moved on from there to talk about actually moving through the graph, right? And so we had the idea of paths, and paths being exactly what we would think they would be, just the order that you go to get from one to another, one vertice to another, and kind of with the idea that there may or may not be a path between every vertice. And then kind of our first actual algorithm, so I would say like up until this point here where we were talking about paths, this is like the core data structure, right? It's the thing that we put stuff in. It's the way it's connected. We talked about the way it was stored. But we weren't really doing anything with it, right? It's just kind of a representation. So we moved into our first attempt at doing something with this data structure, being depth-first search. And the idea being that if we are at some node and we want to try to find another node, there is an approach we can take to navigate through the graph to find that node, if it exists. And with depth-first search in particular, it's kind of what the name describes, right? You can imagine it following like its first, so if you have a node here like D, right? And it's got two options you could initially take. With depth-first search, we'll take the first option, and we're going to follow it all the way through to whatever we're looking for before we come back and try the second option. And that was different from what we introduced next, which was breadth-first search, which was kind of the opposite idea of doing things kind of a layer at a time, which we could also describe as an expanding frontier. So the idea being, wherever you start, you go out a set of nodes, check all their neighbors, then go out another set, check all of those, rather than tunneling straight down. And we did see that there were some differences between doing things one way or the other. One major advantage that stands out for the breadth-first search is that it would give us that shortest path on an unweighted graph, right? Just by the nature of it, it would always give us the minimum number of edges to get from one vertex to another. So we also had some advantages, though, for depth-first search. And ultimately, what it comes down to is that it depends on your data set, right? And that's something we've come back to a lot with graphs, is that when we have a graph and we want to do some operation on the graph, it's always going to come back to what that graph looks like in terms of which algorithms are going to be best on average. So in the worst case, both of these algorithms are the same. The average case, which is usually what we care about more, they can be quite different. So the idea being, like, if you have a data set and you know that, like, your goal is very close in terms of jumps away from your vertices, you might be okay with doing, a breadth-first search. If you know it's very far away, then maybe depth-first search makes sense. It just depends. And so we also talked about how graphs can be either sparse or dense, depending on kind of the ratio of vertices to edges. And then we moved into kind of a little bit of a different mindset about the graph and looking at the graph more in terms of creating this structure that goes over the full graph, right? So when we're doing like depth-first search or breadth-first search, you can definitely traverse the entire graph if you run those without like a target in mind. You run it looking for something that's not there, right? You'll explore the whole graph. But we started talking about a spanning tree, and that the idea being that it is a set of edges that touches every vertex in the graph. And there may be multiple of them for any given graph. And then we focus more on what we actually care about usually, and that's the idea of a minimum spanning tree. And all this does is take into consideration the weights. So we usually have weighted edges, and we're interested in finding the set of weighted edges that has the minimum cost and still goes through every vertex. And so you can imagine why that would be important in any kind of application. It gives you kind of this efficient path through the whole graph. And so we talked about two algorithms for doing that. We talked about Prim's algorithm, and it kind of took a approach of starting at one node and then as a greedy algorithm moving forward, making the best choice at every step. And so here's kind of the pseudocode of that and some of the example that we ran through with doing that. Then we said there's also another approach, which is Kruskal's algorithm. They're both similar in terms of complexity and runtime, but this optimizes on the edges directly. And so there's two choices to do the same thing here. And so then, in last lecture, we started talking about this idea of if we wanted to find the shortest path in terms of weight between two vertices, how would we do that? And we saw that breadth-first search would not always give us that. So like this is kind of a counterexample here where breadth-first search would give us this path here, which is the shortest in number of jumps that we're doing, but in terms of weight, this longer path would actually cost less. And so we saw how Dijkstra's algorithm could be useful there. The idea being that it is also a greedy algorithm that is optimal, and so it makes those local choices over and over, building up that path. And so we talked about the different ways you can implement these, and kind of it matters what's underneath, right? With more of the better computational runtime being when you use a priority queue like a min heap or a Fibonacci heap being a little bit better there. So I want to kind of extend what we were talking about with Dijkstra's algorithm to the topic of negative weights, which you brought up. And I mentioned Bellman-Ford, so I wanted to tell you about negative weights and negative cycles in a little more detail. And so you can kind of get an idea of that. So negative weights can obviously exist on these edges, right? And there are a number of ways of handling negative weights. In some cases, it makes sense to just offset the whole graph and make everything positive. But there are cases where these represent something that would be altered if you were to apply an operation like that. And so typically, like, it'll be like a financial application or something where they represent like a loss or a discount or something that's happening in the graph. And I should say, sometimes graphs are called networks. So if you hear that said, it's unfortunate that a lot of terms collide here, but you will hear people say within the network or within the graph. So, for example, this is kind of like the most basic example here. So if we think of using Dijkstra's algorithm to go from A to C, what we will get there is this path here, right? So we check our neighbors. C is a neighbor, and we'll get this path of going from A to C directly with a cost of 3. And so the problem is that if you look at this graph, that's not actually the lowest cost way to get there, right? If we take into account this negative, because we could go from A to D and then from D to C, which would give us a cost of 2, right? And so Dijkstra's algorithm will fail in this condition. And so does anybody kind of know why Dijkstra's algorithm fails here?
Because it at least use one path and then choose it. It doesn't think of the weight.
Right. So yeah, that's exactly right. Dijkstra's always makes the choice that's in front of it, right? It chooses the best. It doesn't think about, well, maybe like a hop down from here, like I could actually reduce the weight, right? Which is fine when it's positive numbers because they just add up, and that makes sense. But once you get these negative numbers in here, then the greedy approach does not work anymore. So Dijkstra's will not work here. And so the solution to this is an algorithm. I mean, there are several solutions, but kind of the first and the most well-known is called Bellman-Ford. And it can deal with the negative weights, and it can even deal with the negative cycle. But the way that it does that is to actually kind of kill that optimization that Dijkstra's has. So it's not a greedy algorithm. And rather than saying like, okay, I can say, from here to here, I know what the best, cost is, we don't ever do that here. So that has a trade-off, right? So the trade-off being that now we can look at the whole path of every path that's possible and compute an accurate value. And so if we have negative weights in there, we're good. We're still going to find that shortest path that's out there. But this comes with a compromise, obviously, down here in the runtime. So you can be guaranteed it will take order of the number of vertices times the number of edges, because we know it has to look at everything no matter what. It's not able to do that optimization. So kind of another thing that is important to remember about once you introduce negative weights into the picture is you can create a negative cycle, right? So potentially you could design the graph such that actually like looping around keeps lowering your cost, right? And you never get where you're going. You get stuck, so to speak. And Bellman-Ford has a clever way of detecting this. And if you think about graphs in general, you will realize that the number of edges you need for the shortest path is always going to be kind of the number of vertices minus 1 at the highest end. And so what Bellman-Ford does is it continues this relaxation process of these edges, and once it crosses that threshold, if it can still optimize, it will throw it back and say that there's a negative cycle. And in that case, it's kind of considered sometimes unsolvable. It's kind of a strong word, but you have to, if a graph has a negative cycle, you have to make sense of it in context of whatever it is. Yes?
Wouldn't another solve just being that you can only hit one node one time?
Yeah, absolutely. Yeah. So you could just keep track, right? Like in the node data structure or something, or just keep a list, whatever. And when we do hashing, you'll actually see, how quick it is to do something like that. But yeah, that would be another way to detect a cycle easily. Yeah. And so, yeah, the main thing to remember, I guess, about these is that there are algorithms that work on things with negative cycles, but typically the whole point is to like avoid that negative cycle, to segment it out somehow, or to alter it so that it's not causing that negative loop. So there's no like go-to general algorithm for dealing with the negative cycle, but there are, plenty of approaches for detecting it. And so Bellman-Ford will function when the negative weights are there, and if there's a negative cycle, it will throw it back. And so the code's not that much different from what we looked at for Dijkstra's. It's pretty much just that we're going to keep exploring those full paths rather than stopping. All right. So I want to discuss just a couple more graph problems, things that you might want to know about graphs. There are like whole courses, like multiple of them, just about graph theory. So if you're interested in graphs, there's definitely a lot more to learn than what we're going to touch on here. These are the very basics. So I will start by telling you, in case you haven't noticed, that graph theory loves definitions. They love to make up words and define things, and like even certain graphs have names, okay? Like well-known graphs, right? Just these nodes connected in this way is known as whatever. And graph theory is full of that. It's full of that for the graph structures. It's full of that for the algorithms that get applied. And it turns out it's not just for kind of like to be annoying or anything, but because like once you solve one of these problems, then you can talk about it in the scope of bigger problems. So there is a lot to know about graph algorithms and that whole field. So I'll go ahead and introduce some more definitions while we talk about this. So we're going to talk about Euler paths first. And so you can imagine a lot of examples here. But in this case, like we have a snowplow driver. And imagine that the graph, the edges are streets, the nodes are just intersections, right? And so the goal is that the driver wants to drive on all of the streets, but only wants to go down each street once. So wants to cover all of these edges, but only visit them once. And so that path that lets you do that is called an Euler path. Euler was a person. He was concerned with bridges in what is now Kaliningrad, Russia, I think. So it comes from a long time ago, the 1800s, I think, kind of the beginning of graph theory. But this idea that you can either have an Euler path in your graph or not, right? They might not all have them. And so there actually turns out to be a trick to this, to finding this out kind of quickly. And so it's just a rule that you'll have an Euler path if you contain at most two vertices with an odd degree. And so this is why I say graph theory loves definitions, right? Because we've got like, now degree, we have to remember degree is like the number of things coming in or going out. And so this kind of gets layered on. But this is a great thing to know in general because that's pretty easy, right? Like you can look at any graph and assess that to know if it's going to be able to have that path. And so these are some examples in which cases there are or are not Euler paths. And I've got them listed here. For the sake of time, I will not go through them. Now you can take this a little bit further. Same problem, right? But we're going to add this criteria here to say we have to end and start at the same point. So you could see how this could optimize something even like driving the snowplow, right? If you can only cover everything once and end up where you started, you've probably saved a lot of resources and you've completed the task. So it turns out we actually can determine if an Euler circuit exists, which is what that's called. following some of these same rules. And so if all the vertices have an even degree, then we know that there will be an Euler circuit. And not all graphs have them, obviously. Similar thing here. These are just some examples. Pretty easy to parse. So with all of that said, computationally, these are not bad to find, right? This is linear time. Let's move on to something better. So let me introduce Hamiltonian paths and circuits. It's a similar idea, but instead of the edges, we're concerned about the vertices, right? So you can imagine if you needed to deliver something to like a bunch of businesses or something, right? You need to visit every location, but you don't necessarily need to go down every street, through every intersection. You don't care about that so much. And so we have the two ideas. We have the path, which is where you visit each vertex exactly once, but it doesn't matter where you start or end. And then the circuit, which is where we visit each vertex once, and we start and end at the same vertex. Okay. So unlike the Euler paths and circuits, Hamiltonian paths and circuits are difficult to find. There's no trick that we know of, and computationally, it's a hard problem. So also, to add to this, usually it's not enough just to solve this Hamiltonian circuit problem. Usually we want to optimize it further, based on like edge weights or something. And so here are some examples of having a circuit and not having a circuit. What's more interesting than that is the difficulty to find those circuits on an arbitrary graph. We do not know of a polynomial time algorithm for finding those, which puts us in territory that's very scary, like v factorial. So if you kind of think about that, you can't really have a lot of vertices and do that approach. You can use dynamic programming. You can get this a little bit better. That's still awful. V squared times 2 to the v. Not great if you remember early on when we talked about kind of the running times of things. So this leads into, how many people have heard of the traveling salesman problem, traveling salesperson problem? We'll call it TSP so we don't have to worry about it. But it's a pretty famous problem. There's a movie called Traveling Salesman, I think. It's about computer science, which is weird. So you might want to check that out. Famous problem, right? And the idea is you've got a person who is selling things, right? And they need to go to all these cities. So you've got a graph of all the cities they need to visit. You've got pathways between those cities. Maybe it's like flights or roads, whatever it is. There's some cost associated with it. And what you want to do is start at one point, and you never want to visit a city twice. You want to arrive back at where you started, and you want to minimize the cost here. So you can think about applying this to any kind of like logistics problem, right? Like if you think about like national or worldwide like concert tours, right? This is the exact problem, right? You have cities, you have locations where you want to hold these events. You have to move a ton of stuff and people between them. There's some cost associated with that. So what is the best ordering to do that in? And you can optimize on all kinds of things. Typically cost would be what you would be optimizing on. It's a hard problem. So it's very much related to this basic idea of this Hamiltonian circuit, but we've added on the optimization for the weights. And so it is that problem with an optimization problem tacked on. So from what we saw just with the basic circuit, you know that if we were to brute force this, if we were to just try to enumerate all of the possible like orders, right, in factorial, so it adds up very quickly. So I think, yeah, like one estimate, and this depends on a lot of things, but like you can maybe do like 10 cities or 10 vertices, right, before this becomes impossible. So there are some optimizations you can make. Again, getting that familiar one there, maybe get you up to like 20 vertices, still not great. And you can use some clever techniques to get more vertices, a few more, for kind of the same runtime there of n factorial. But it turns out that this problem, at least as far as we know, can't be solved in polynomial time. So anybody guess, like, what do you do if you are trying to set up your nationwide tour of concerts and want to optimize this?
Just take like the first available short path. You don't evaluate all the possible paths. You're just like, well, this one seems the shortest, we'll go that way.
Right. So it turns out that's exactly what happens. Real-world applications, people can usually say, what would be good enough, right? We don't need the best, usually. We just need pretty good. And so all of the techniques that deal with this kind of problem, and to kind of spoil this for you, a lot of graph problems come back to this. You can convert problems to other problems called reduction. You'll cover that like in analysis of algorithms a lot. And essentially, when they come back to this, that's bad news. It's amazing the number of things we can't actually compute like fully. We end up making a lot of like heuristic guided guesses that are very good. And usually they're really good for like what we actually want to do in the world, but they're by no means like the answer. We don't know because we can't explore the full space. And so that will bring us into kind of talking a little bit about complexity. And I think what I'll do on that is I'm going to wait since we're here. We'll do like 10 minutes of talking about complexity. You'll do a ton more in an algorithms course about it. But I do want to touch on it so you kind of think about it in terms of the graph structures that we've been looking at and how that works with these problems, which are pretty real problems that get applied in a lot of ways. So with that said, we'll see you guys on Friday, and we will get challenge 4 set up.